Picture this. It's October 19th, 2017. A Canadian astronomer named Robert Warwick is reviewing routine observations from the Pan-STARRS telescope in Hawaii, sifting through what should have been another ordinary night of cosmic surveillance. But something catches his eye. A faint speck of light moving through space at an impossible speed. Not the leisurely drift of an asteroid, not the predictable arc of a comet. This object is screaming through our solar system at 196,000 miles per hour, carrying with it mysteries that would challenge everything we thought we knew about the cosmos. What Warwick had discovered would soon be named Oumuamua, a Hawaiian word meaning messenger from afar arriving first. And for the next 7 years, it would become the most controversial, most debated, most enigmatic object in modern astronomy. Scientists would propose it was made of hydrogen ice. Others suggested it was a fragment of an alien world. A Harvard professor would claim it might be extraterrestrial technology. Each theory would be challenged, debated, and ultimately found wanting. But now, as we settle into this journey together, forget about time for a moment. Pour yourself something warm, get comfortable, because what we're about to explore together will take us to the very edges of scientific understanding. The story of Oumuamua is not just about a strange visitor from another star system. It's about how science works when faced with the truly inexplicable, how brilliant minds grapple with phenomena that don't fit our carefully constructed models of reality. And after 7 years of speculation, controversy, and heated scientific debate, we may finally have our answer. When Oumuamua first appeared in our telescopes, astronomers initially classified it as a comet. This made sense, given its trajectory from beyond our solar system. But within days, that classification would prove problematic. Comets, as they approach the sun, develop spectacular tails as solar radiation sublimates ice and dust from their surfaces. They become bright, dramatic displays visible even to the naked eye. Oumuamua, however, remained stubbornly tailless, so astronomers reclassified it as an asteroid. But this too would prove inadequate. Asteroids follow predictable paths dictated by gravitational forces. They don't mysteriously accelerate without visible cause. Yet as telescopes tracked Oumuamua's path through the solar system, something unprecedented happened. The object began to speed up. This wasn't the gradual acceleration of a spacecraft using continuous thrust. It was a subtle but persistent deviation from the path that gravity alone should have dictated. The acceleration was tiny, roughly 1,000th of the gravitational force our sun exerted on the object. But it was real, it was measurable, and it was utterly inexplicable. Dr. Marco Micheli, an astronomer at the European Space Agency, who led the initial analysis of Oumuamua's acceleration, would later describe the discovery as unlike anything they had encountered. The object was pushing against the sun's gravitational pull with a force that seemed to have no visible source. By the time astronomers had gathered enough data to understand what they were looking at, Oumuamua was already departing our solar system, racing toward the constellation Pegasus at a speed that would carry it beyond Neptune's orbit within 4 years. The window for detailed observation had essentially closed before scientists even realized how extraordinary their visitor truly was. But the data they had collected painted a picture of an object that defied every category in our astronomical taxonomy. Oumuamua was neither comet nor asteroid. It was something else entirely. The physical characteristics of Oumuamua read like a catalog of astronomical anomalies. Analysis of its brightness variations suggested an object between 100 and 400 meters in length, but with an aspect ratio unlike anything in our solar system. Where typical asteroids might be twice as long as they are wide, Oumuamua appeared to be at least 10 times longer than it was wide. Some models suggested it might be even more extreme, resembling a cosmic cigar or perhaps a flattened disk tumbling through space. This elongated shape immediately raised questions. In our solar system, gravitational forces and collisional processes tend to create objects that are roughly spherical or, at most, mildly elongated. The extreme proportions of Oumuamua suggested formation processes or evolutionary history unlike anything we had encountered. The object's surface composition added another layer of mystery. Spectroscopic analysis revealed a reddish coloration similar to objects in the outer reaches of our solar system, suggesting a surface that had been irradiated by cosmic rays for hundreds of millions of years. This supported the idea that Oumuamua had indeed wandered the galaxy for eons before its chance encounter with our solar system. But perhaps most puzzling was what Oumuamua didn't show. Despite its close approach to the Sun, bringing it within 23 million miles of our star, the object exhibited no signs of the outgassing that characterizes comets, no visible coma of gas and dust, no jets of sublimating material, no debris trail that telescopes could detect, yet something was clearly acting on the object. The acceleration, though small, was undeniably present in the tracking data. Some invisible force was pushing Oumuamua away from the Sun, gently but persistently altering its trajectory. Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory, who analyzed the object's orbital mechanics, described the situation as unprecedented. They were observing an effect that suggested outgassing, but without any of the visible signs that should accompany such a process. It was like hearing a sound with no apparent source. When confronted with an object that didn't fit existing categories, the scientific community did what it does best. It began generating hypotheses, some conventional, some exotic, and some that would prove deeply controversial. The first attempts at explanation focused on conventional cometary processes. Perhaps Oumuamua was outgassing material that was simply too faint to detect. Maybe it was composed of materials that sublimated in ways our instruments couldn't observe. Carbon monoxide ice was proposed, as it would be invisible to most telescopes while still providing the thrust needed to explain the acceleration. But these conventional explanations faced significant problems. The amount of undetected outgassing required to produce the observed acceleration was substantial. Calculations suggested that a significant fraction of Oumuamua's surface would need to be actively sublimating, yet multiple powerful telescopes detected no trace of such activity. As conventional explanations proved inadequate, more exotic theories emerged. In 2020, scientists proposed that Oumuamua might be composed of molecular hydrogen ice formed in the extreme cold of giant molecular clouds. This would explain both the object's unusual shape and its mysterious acceleration, as hydrogen ice would sublimate at the very low temperatures found in space. The hydrogen ice theory had elegant appeal. Giant molecular clouds, the stellar nurseries where new stars are born, can reach temperatures just a few degrees above absolute zero. Under such conditions, hydrogen gas might condense into solid ice, potentially forming objects with the unusual properties observed in Oumuamua. But even this theory faced challenges. Follow-up studies suggested that hydrogen ice objects would be extremely fragile, unlikely to survive the millions or billions of years needed to travel between star systems. The heating from starlight during such a journey would gradually destroy any hydrogen ice object, leaving nothing to reach our solar system. Other theories proliferated. Perhaps Oumuamua was a fragment of nitrogen ice, similar to the surface material found on Pluto, broken away from some distant world. Maybe it was composed of exotic materials formed under conditions that don't exist in our solar system. Each theory addressed some aspects of Oumuamua's behavior while failing to explain others. But it was the most controversial theory of all that would capture public attention and divide the scientific community. Dr. Abraham Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University, has never been one to shy away from unconventional ideas. Former chair of Harvard's Astronomy Department and director of the Institute for Theory and Computation, Loeb has built a career on asking questions that others might consider too radical for serious scientific discourse. When Loeb examined the data on Oumuamua, he reached a conclusion that would make him one of the most controversial figures in modern astronomy. In his view, the object's properties were not just unusual, they were consistent with artificial origin. In short, Oumuamua might be alien technology. The logic of Loeb's argument was straightforward. even if its implications were extraordinary. The object's extreme elongation matched what might be expected from a solar sail, a propulsion system that uses radiation pressure from starlight to generate thrust. The mysterious acceleration could be explained by sunlight pushing against a large, thin surface. The lack of outgassing made perfect sense if the object was artificial rather than composed of sublimating ice. Loeb's hypothesis gained additional support from what the object didn't do. Unlike natural comets, Oumuamua showed no signs of tumbling or rotation changes that would be expected if jets of gas were randomly erupting from its surface. Its acceleration was smooth and consistent, more like what might be expected from a designed propulsion system than from chaotic natural processes. In his 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, Loeb laid out his case in detail. He argued that the scientific community's resistance to considering artificial origin was not based on evidence, but on an institutional bias against ideas that seemed too extraordinary. The book became a bestseller, but Loeb's ideas were met with fierce resistance from much of the astronomical community. Critics argued that he was jumping to conclusions, that invoking alien technology was premature when more conventional explanations hadn't been fully explored. Dr. Karen Meach, who led the initial observational campaign of Oumuamua, publicly criticized Loeb's approach, suggesting that he was promoting speculation rather than rigorous science. But Loeb remained undaunted. He pointed out that extraordinary claims require extraordinary evidence, but they also deserve extraordinary attention. If there was even a small possibility that Oumuamua represented our first encounter with alien technology, shouldn't the scientific community investigate that possibility rather than dismissing it out of hand? The debate over Oumuamua became as much about the philosophy of science as about the object itself. How should researchers approach phenomena that don't fit existing models? When is it appropriate to consider radical explanations? What constitutes sufficient evidence for extraordinary claims? As the scientific community grappled with these questions, Oumuamua continued its journey outward, growing fainter with each passing month until it could no longer be observed by even the most powerful telescopes. The window for gathering new data had closed, but the mystery remained. While the scientific community debated alien visitors and exotic ice compositions, two researchers were pursuing a much more subtle line of investigation. Dr. Jenny Bergner at UC Berkeley and Dr. Daryl Seligman at Cornell University were examining a possibility that had been largely overlooked in the rush to propose exotic explanations. Bergner's expertise was in astrochemistry, the study of chemical reactions that occur in the extreme environments of space. She understood how high-energy radiation affects matter in the vacuum between stars, how cosmic rays can fundamentally alter the molecular structure of objects over millions of years of interstellar travel. Seligman, ironically, had been one of the proponents of the hydrogen ice theory for Oumuamua, but as that theory faced mounting criticism, he began to reconsider the problem from a different angle. What if Oumuamua wasn't composed of exotic materials? What if it was, in fact, a relatively ordinary comet that had been transformed by its long journey through interstellar space? The insight that would ultimately solve the Oumuamua mystery came from considering a process that had been documented in laboratory experiments decades earlier, but which had never been applied to understanding interstellar objects. When water ice is exposed to high-energy radiation, the kind that pervades interstellar space, the water molecules don't simply remain intact. The energetic particles break chemical bonds, liberating hydrogen atoms that can then combine to form molecular hydrogen gas. This process, known as radiolysis, had been studied extensively in the 1970s and 1980s by researchers investigating the effects of radiation on ice. But here was the crucial insight. In the cold vacuum of space, this newly formed hydrogen gas doesn't simply escape. Instead, it becomes trapped within the ice matrix, creating a kind of pressurized system that can persist for millions of years. Bergner and Seligman realized that this process could transform an ordinary water-rich comet during its journey through interstellar space. Cosmic rays, the high-energy particles produced by supernovae and other violent cosmic events, would gradually convert portions of the comet's water ice into trapped hydrogen gas. By the time such an object reached our solar system, it might contain substantial amounts of molecular hydrogen embedded within its ice structure. The beauty of the Bergner-Seligman model lay in its simplicity. As Oumuamua approached the sun, solar heating would warm its surface, causing the trapped hydrogen gas to expand and escape. But unlike the heavier molecules typically ejected by comets, molecular hydrogen is extremely light. The escaping gas would produce thrust sufficient to explain Oumuamua's acceleration, but wouldn't carry enough dust and debris to create a visible coma or tail. The theory explained not just the mysterious acceleration, but virtually every puzzling aspect of Oumuamua's behavior. The lack of visible outgassing made perfect sense. Hydrogen gas is colorless and carries minimal dust. The smooth, consistent nature of the acceleration was exactly what would be expected from the gradual release of gas from a warming surface. Even the object's unusual shape could be explained by the differential heating and gas release across its surface. Calculations showed that only about 6% of Oumuamua's surface would need to be releasing hydrogen to produce the observed acceleration. This was far less than would be required for conventional water ice outgassing, making it much more plausible that such a process could occur without creating visible signs. The model also explained why Oumuamua appeared so different from 2I Borisov, the second interstellar object discovered in 2019. While Borisov looked like a conventional comet with a bright coma and tail, it had spent far less time in interstellar space than Oumuamua. The radiolysis process requires millions of years of cosmic ray bombardment to build up significant quantities of trapped hydrogen. When Bergner and Seligman published their findings in the journal Nature in 2023, the response from the scientific community was notably different from the reception given to previous theories. Here was an explanation that required no exotic materials, no alien technology, and no unprecedented physical processes. It invoked only well-understood chemistry and physics applied to the unique environment of interstellar space. Dr. Alan Fitzsimmons at Queen's University Belfast, who had been tracking Oumuamua since its discovery, described the hydrogen outgassing model as pulling all the loose threads together into a coherent picture. Dr. Marco Micheli at the European Space Agency called it the most convincing explanation yet proposed, but the scientific process doesn't end with a single compelling paper. Other researchers began examining the model in detail, testing its assumptions and exploring its implications. Not everyone was convinced by the hydrogen outgassing theory. Dr. Avi Loeb, the Harvard professor who had proposed alien technology, quickly published a response questioning key aspects of the Bergner-Seligman model. Working with Dr. Thiem Hoang from Korea University of Science and Technology, Loeb argued that the calculations of Oumuamua's surface temperature were flawed. When hydrogen gas escapes from a surface, it carries away thermal energy, cooling the object through a process called evaporative cooling. Loeb and Hoang contended that this cooling effect had been neglected in the original calculations. Their analysis suggested that evaporative cooling would reduce Oumuamua's surface temperature by a factor of 9, making the hydrogen outgassing far less efficient. To produce the observed acceleration under these cooler conditions would require that virtually all of the object's water had been converted to hydrogen, essentially turning Oumuamua back into a pure hydrogen object, which brought the theory full circle to the hydrogen ice scenario that had already been discredited. The debate revealed the inherent challenges of studying an object that can no longer be observed. Every model and calculation relies on assumptions about Oumuamua's composition, structure, and thermal properties. Small changes in these assumptions can lead to dramatically different conclusions about the object's behavior. Loeb also pointed to other aspects of Oumuamua that the hydrogen outgassing model didn't fully address. The object's extreme elongation remained puzzling. Why would an interstellar comet develop such unusual proportions? The lack of any detectable changes in rotation or tumbling was also curious, as most comets show such changes when they begin outgassing. But perhaps most significantly, Loeb argued that the scientific community's eagerness to embrace the hydrogen outgassing theory reflected a bias toward conventional explanations, even when those explanations required complex scenarios and specific conditions. In his view, the alien technology hypothesis remained viable and deserved serious consideration rather than reflexive dismissal. The ongoing debate highlighted the challenges of doing science at the frontiers of knowledge. When dealing with truly unprecedented phenomena, researchers must balance healthy skepticism against openness to radical possibilities. The history of science is filled with discoveries that initially seemed impossible or absurd, from continental drift to quantum mechanics to black holes. While scientists continued to debate the nature of our first interstellar visitor, new discoveries were expanding our understanding of these cosmic wanderers. In December 2019, amateur astronomer Gennady Borisov spotted another interstellar object approaching the Sun. Unlike Oumuamua, 2I Borisov looked exactly like what astronomers expected an interstellar comet to look like. Borisov displayed a bright, obvious coma and tail as it approached the Sun. Its composition appeared similar to comets in our own solar system, with abundant water ice and familiar organic compounds. In every respect except its hyperbolic trajectory, Borisov seemed unremarkable. The contrast with Oumuamua was striking. Here were two objects from interstellar space, yet they appeared completely different. If Borisov represented typical interstellar comets, what did that make Oumuamua? The discovery of Borisov lent support to the idea that Oumuamua was indeed unusual, even among interstellar objects. Perhaps its long journey through space had genuinely transformed it into something unprecedented, or perhaps the universe contained a wider variety of interstellar objects than anyone had imagined. More recently, in 2025, astronomers identified a third interstellar visitor, 3I/ATLAS. Early observations suggested it too might be a comet, actively releasing water vapor as it approached the Sun. The growing catalog of interstellar objects was beginning to provide context for understanding Oumuamua. Dr. Shokruz Kakarov and Dr. Avi Loeb published research tracing the origins of all three known interstellar visitors. Their calculations suggested that these objects represented different populations of cosmic wanderers. 3I/ATLAS appeared to be ancient, perhaps ejected from its home system over 3 billion years ago. Oumuamua seemed younger by comparison, only about 1 billion years old. The diversity suggested that interstellar objects are ejected from planetary systems throughout the galaxy's history. The debate over Oumuamua has inspired new approaches to searching for signs of technological civilization in the cosmos. Loeb established the Galileo Project, a research initiative specifically designed to look for evidence of extraterrestrial technology using rigorous scientific methods. The project represents a departure from traditional SETI approaches, which focus primarily on radio signals. Instead, Galileo seeks physical artifacts, spacecraft, probes, or debris that might indicate the presence of technological civilizations. Oumuamua, regardless of its ultimate nature, demonstrated that such objects could pass through our solar system and be detected by existing telescopes. The project has deployed telescopes capable of tracking small, fast-moving objects in unprecedented detail. If another Oumuamua-like visitor appears, researchers will be prepared to gather far more comprehensive data than was possible in 2017. But the Galileo project faces the same challenge that has plagued Oumuamua research. Distinguishing between natural and artificial objects requires understanding natural processes extremely well. Every unusual property must be evaluated against the backdrop of what's possible through conventional astrophysical mechanisms. The hydrogen outgassing theory for Oumuamua, if correct, illustrates how exotic behavior can emerge from well-understood but rarely considered processes. The transformation of water ice by cosmic ray bombardment over millions of years creates conditions that simply don't exist in our solar system. objects shaped by such processes might naturally appear artificial to observers familiar only with local phenomena. The story of Oumuamua extends far beyond the mystery of a single interstellar visitor. It reflects the challenges faced by modern astronomy as our instruments become powerful enough to detect phenomena that challenge existing theoretical frameworks. The discovery of exoplanets has revealed planetary systems utterly unlike our own. The detection of fast radio bursts and other transient phenomena has shown that the universe regularly produces events of staggering power and brevity. Oumuamua represents another example of the universe's capacity to surprise us. Perhaps more importantly, the Oumuamua controversy illustrates how science approaches the unknown. The process has been messy, contentious, and sometimes personal. Researchers have proposed ideas ranging from the conventional to the radical, each contributing pieces to our understanding of what's possible in the cosmos. The hydrogen outgassing theory may prove to be correct, but it took years of investigation, debate, and refinement to develop. Even now, questions remain about the details of the process and its applicability to other interstellar objects. Science progresses not through sudden revelations, but through the gradual accumulation of evidence and understanding. The debate has also highlighted the importance of keeping an open mind while maintaining rigorous standards. Loeb's willingness to consider artificial origin, regardless of whether it proves correct, has pushed the community to examine their assumptions and biases. The possibility of technological artifacts in space is not inherently less scientific than the possibility of exotic ice compositions. Our understanding of interstellar visitors is about to expand dramatically. The Vera C. Rubin Observatory in Chile is scheduled to begin operations in 2025, conducting the Legacy Survey of Space and Time. This survey will monitor the entire visible sky every few nights, providing unprecedented capability to detect fast-moving objects. Calculations suggest the survey should discover several interstellar objects each year, potentially dozens if such visitors are more common than current estimates suggest. Each new discovery will provide additional data points for understanding the population of objects wandering between the stars. The European Space Agency's Comet Interceptor mission, scheduled for launch in the coming years, will position itself beyond Earth's orbit, ready to redirect toward any promising interstellar visitor. Unlike the situation with Oumuamua, where scientists could only observe from a distance as the object departed, future missions might achieve close-up encounters. These upcoming observations will test the hydrogen outgassing theory against new examples. If the model is correct, some fraction of interstellar comets should show similar properties to Oumuamua: acceleration without visible outgassing, unusual shapes, and other characteristics that now seem mysterious. But the survey might also reveal objects that don't fit any current theories. The universe has already surprised us with Oumuamua. There's no reason to assume that all interstellar visitors will conform to our current understanding of what's possible. As we've followed the journey from Oumuamua's discovery to the current state of understanding, we've witnessed science at both its most frustrating and most inspiring. The inability to definitively resolve the object's nature reflects the fundamental challenges of studying phenomena at the limits of our observational capabilities. Yet this same limitation has driven remarkable creativity in developing theoretical models and experimental approaches. Researchers have proposed scenarios involving processes that operate over millions of years and distances measured in light years. They've considered chemical reactions occurring at temperatures just above absolute zero and mechanical forces so subtle they barely perturb an object's trajectory. The hydrogen outgassing theory represents a synthesis of laboratory experiments from the 1970s, cosmic ray physics, thermodynamics, and orbital mechanics. It's a testament to the interconnected nature of scientific knowledge, where insights from seemingly unrelated fields combine to illuminate new phenomena. Whether this theory ultimately proves correct, it has already accomplished something important. It has demonstrated that Oumuamua's properties, however unusual, can potentially be explained through natural processes. The object doesn't require exotic materials or revolutionary physics. It may simply require a deeper appreciation of how familiar processes operate under unfamiliar conditions. The story of Oumuamua is far from over. As new interstellar objects are discovered and studied, they will provide crucial tests of the various theories proposed to explain our first visitor. The hydrogen outgassing model makes specific predictions about the properties of interstellar comets that can be verified or falsified by future observations. If hydrogen outgassing is indeed common among objects that have spent millions of years in interstellar space, we should see similar behavior in other visitors. Objects with longer interstellar travel times should show more pronounced effects, while those with shorter journeys should appear more conventional. The upcoming surveys will also reveal whether Oumuamua is truly unusual or if objects with similar properties are relatively common. This statistical information will be crucial for understanding whether special explanations are needed or if Oumuamua represents one example from a diverse population of interstellar wanderers. But perhaps the most important legacy of the Oumuamua controversy will be its demonstration of how science grapples with the truly unprecedented. The discovery has shown that our solar system is not isolated, that visitors from other stellar systems pass through regularly, carrying information about conditions and processes in distant regions of the galaxy. These objects represent libraries of information about the formation and evolution of planetary systems, the chemistry of interstellar space, and the dynamics of galactic environments. Each visitor offers a unique perspective on cosmic history, having traveled paths and experienced conditions that no Earth-based laboratory can replicate. The evolution of our understanding of Oumuamua provides a masterclass in how modern science actually works. The process has been neither linear nor tidy. Initial observations led to classifications that proved inadequate. Early theories were proposed, challenged, and refined or abandoned. New models emerged that seemed promising but faced unforeseen difficulties. Throughout this process, the scientific community has demonstrated both its greatest strengths and its most human limitations. The willingness to propose radical hypotheses like alien technology shows science at its most creative and open-minded. The sometimes harsh criticism of such ideas reflects the community's commitment to evidence-based reasoning. The hydrogen outgassing theory may ultimately prove to be correct, but its acceptance hasn't ended the scientific process. Researchers continue to refine the model, test its predictions, and explore its implications. Science is not a destination, but a journey, a continuous process of improving our understanding of the natural world. The controversy over Oumuamua has also demonstrated the importance of interdisciplinary collaboration. The solution, if the hydrogen outgassing theory proves correct, required insights from chemistry, physics, astronomy, and planetary science. No single field of study contained all the pieces needed to solve the puzzle. As we conclude this journey through the mystery of Oumuamua, it's worth reflecting on what 7 years of investigation have taught us. We've learned that interstellar space is not the empty void we once imagined, but a dynamic environment where complex chemical and physical processes shape objects over vast periods of time. We've discovered that our solar system is regularly visited by objects from other stellar systems, each carrying unique information about cosmic conditions and processes. We've seen how objects can be transformed by journeys lasting millions of years, developing properties that seem impossible based on our local experience. Perhaps most importantly, we've witnessed how science approaches the genuinely unknown. The process has been contentious, uncertain, and sometimes uncomfortable, but it has also been creative, collaborative, and ultimately productive. Our understanding of Oumuamua may still be incomplete, but it's far more sophisticated than it was in 2017. The hydrogen outgassing theory offers an elegant explanation for most of Oumuamua's puzzling properties. It requires no exotic materials, no unprecedented physics, and no extraordinary assumptions. It simply applies well-understood processes to extreme conditions and timescales. Yet questions remain. The theory doesn't fully explain Oumuamua's unusual shape or address all aspects of its behavior. Future discoveries may require further refinements or even completely new approaches. Science is a process of continuous revision and improvement. Even if the hydrogen outgassing theory proves correct, Oumuamua will retain its significance as the object that introduced us to the complexity and diversity of interstellar space. It was our first glimpse of the cosmic wanderers that populate the galaxy, objects shaped by processes and environments that exist nowhere in our solar system. The discovery has opened new fields of research and inspired new approaches to understanding the cosmos. The search for interstellar objects is now a major focus of astronomical surveys. The possibility of technological artifacts in space is being investigated with unprecedented rigor. Our conception of what's possible in the universe has been expanded, but perhaps Oumuamua's greatest contribution has been to remind us of our cosmic context. We live in a galaxy containing hundreds of billions of stars, many of which host planetary systems. The formation and evolution of these systems inevitably ejects material into interstellar space, creating a population of wandering objects that occasionally pass through our solar system. Each of these visitors carries information about conditions in distant regions of the galaxy. They are messengers, as the name Oumuamua suggests, bringing news from realms we cannot yet explore directly. By studying these objects, we gain insights into the diversity of cosmic environments and the processes that shape matter on galactic scales. As we look ahead, the prospects for understanding interstellar visitors have never been better. New telescopes and surveys will detect many more objects like Oumuamua, providing the statistical context needed to understand whether our first visitor was typical or exceptional. Advanced spectroscopic techniques will allow detailed analysis of composition and structure, testing the predictions of various theoretical models. Space missions may achieve close encounters with future visitors, gathering data that was impossible to obtain for Oumuamua. But perhaps most importantly, each new discovery will refine our understanding of what's possible in the universe. The cosmos has a remarkable ability to surprise us, producing phenomena that challenge our theoretical frameworks and expand our conception of reality. Oumuamua has taught us to expect the unexpected. It has shown us that the universe contains objects and processes that don't fit neatly into our existing categories. As we continue to explore the cosmos, we can be certain that more surprises await. The story of Oumuamua is ultimately a story about the frontier of knowledge, about humanity's ongoing quest to understand our place in the cosmos. It's a reminder that despite our technological sophistication and scientific knowledge, we still inhabit a universe full of mystery and wonder. 7 years after its discovery, Oumuamua continues its journey toward the constellation Pegasus, carrying with it the secrets of its origin and composition. We may never know its true nature with absolute certainty, but in trying to understand this mysterious visitor, we've learned something profound about both the cosmos and ourselves. The universe is vast, ancient, and filled with processes operating on scales of space and time that dwarf human experience. Yet, through careful observation, creative thinking, and collaborative effort, we can begin to comprehend even the most exotic phenomena. Oumuamua may have departed our solar system, but its legacy of discovery continues, and somewhere in the darkness beyond Neptune's orbit, our first confirmed interstellar visitor continues its lonely journey through the void, a messenger from afar that changed our understanding of what's possible in the cosmos. Whatever its ultimate nature, transformed comet, exotic ice, or something we haven't yet imagined, Oumuamua has earned its place as one of the most significant astronomical discoveries of our time. The mystery may never be fully resolved, but in the attempt to understand it, we've taken another step forward in humanity's greatest adventure, the quest to comprehend the universe we call home. Yet the story of Oumuamua extends far beyond a single mysterious object. Its discovery has fundamentally altered our understanding of the galactic environment in which our solar system exists. For decades, astronomers had theorized about the existence of interstellar objects, but Oumuamua provided the first concrete proof that such visitors regularly pass through our cosmic neighborhood. The implications are staggering when we consider the numbers involved. If Oumuamua represents a typical example of interstellar objects, calculations suggest that at any given moment there might be dozens or even hundreds of such visitors within our solar system, most too small or too distant to detect with current instruments. We are not isolated inhabitants of a single stellar system, but participants in a vast galactic ecosystem where material flows freely between star systems. This realization has profound implications for our understanding of how planetary systems form and evolve. The ejection of objects like Oumuamua during the chaotic early phases of planetary formation means that the building blocks of worlds are constantly being redistributed throughout the galaxy. Every star system contributes to and receives from this cosmic recycling program. The hydrogen outgassing theory, if correct, has opened an entirely new chapter in our understanding of interstellar chemistry. The idea that cosmic rays can fundamentally alter the molecular structure of objects over millions of years suggests that interstellar space is not a passive medium, but an active chemical laboratory. Consider the implications. An object like Oumuamua, wandering through the galaxy for hundreds of millions of years, experiences conditions that exist nowhere in our solar system. The constant bombardment by high-energy particles gradually breaks down complex molecules and reforms them in ways that would be impossible under terrestrial conditions. Dr. Jennifer Bergner's research into this process has revealed that the transformation is not random, but follows predictable patterns. Water molecules, when struck by cosmic rays, preferentially break apart at specific chemical bonds. The liberated hydrogen atoms can then recombine in the cold vacuum of space, forming molecular hydrogen that becomes trapped within the ice matrix. This process creates what might be called cosmic vintage, objects whose chemical composition reflects not just their original formation conditions, but also their journey through interstellar space. Each cosmic ray impact leaves a molecular fingerprint, a record of the object's passage through different regions of the galaxy with varying radiation environments. The implications extend to our understanding of how organic molecules might survive and evolve during interstellar journeys. If simple molecules like water can be transformed over cosmic timescales, what happens to more complex organic compounds? Could the building blocks of life be created, destroyed, or transformed during the long journey between star systems? Oumuamua has forced us to adopt a truly galactic perspective on planetary system evolution. The object's estimated age of 1 billion years means it has completed roughly 4 full orbits around the galactic center since its ejection from its parent system. During this journey, it has passed through regions of space with vastly different properties: dense molecular clouds, stellar association regions, and the relatively empty voids between spiral arms. Each environment would have left its mark on the object. Passage through dense molecular clouds would expose it to different types of radiation and potentially different chemical environments. Encounters with other star systems, while rare, might gravitationally perturb its trajectory or expose it to different stellar radiation fields. The fact that Oumuamua survived this billion-year journey intact suggests remarkable durability. It also implies that the object we observed in 2017 was fundamentally different from the one that was originally ejected from its parent system. The Oumuamua that visited us was not a pristine relic of another world, but a seasoned traveler shaped by eons of cosmic evolution. This perspective changes how we think about the relationship between star systems. Rather than isolated islands of matter orbiting individual stars, planetary systems exist within a connected galactic ecosystem. Material ejected during planet formation in one system can eventually be incorporated into planets forming around other stars millions or billions of years later. The concept has profound implications for astrobiology. If life-bearing material can survive interstellar journeys, then life itself might spread throughout the galaxy through a process of natural panspermia. Oumuamua, regardless of its composition, demonstrates that objects can indeed travel between star systems and remain intact. The discovery of Oumuamua marked the beginning of what might be called the interstellar detection revolution. Prior to 2017, no confirmed interstellar object had been observed within our solar system. Now, just 8 years later, we have confirmed at least 3 such visitors, with more discoveries expected as observational capabilities improve. The Vera C. Rubin Observatory represents the next major leap in our ability to detect these cosmic wanderers. With its unprecedented combination of large aperture, wide field of view, and rapid cadence observations, the observatory will survey the entire visible sky every 3 nights. Computer models suggest this survey could detect between 1 and several dozen interstellar objects each year, but detection is only the beginning. Each new discovery will provide additional data points for understanding the population characteristics of interstellar objects. Are most of them comet-like, as suggested by 2I/Borisov and 3I/ATLAS, or was Oumuamua's unusual properties more common than initially thought? The statistical analysis of multiple objects will also help resolve some of the ongoing controversies about Oumuamua. If hydrogen outgassing is a common phenomenon among interstellar comets, we should observe similar acceleration patterns in other visitors. If Oumuamua's extreme elongation is typical, it might suggest formation or evolution processes that we don't yet understand. Perhaps most importantly, a larger sample size will help distinguish between natural and potentially artificial objects. Loeb's argument for considering artificial origin gains strength from the fact that Oumuamua appears so different from typical solar system objects. But if interstellar objects generally show unusual properties due to their unique evolutionary history, then Oumuamua's strangeness becomes less significant. The limited observational window for Oumuamua has inspired serious proposals for interstellar interception missions. Several research groups have developed detailed mission concepts that could reach the object using existing or near-future rocket technology, despite its current distance of over 100 astronomical units from Earth. The most ambitious proposal, known as Project Lyra, envisions a spacecraft launched in the late 2020s that would use a complex series of gravitational assists from Jupiter and the Sun to accelerate to the extreme velocities needed to catch up with Oumuamua. The mission would require unprecedented precision in trajectory planning and would push our space technology to its absolute limits. Such a mission would face extraordinary challenges. The spacecraft would need to function autonomously for over a decade while traveling farther from Earth than any previous human-made object. It would need to survive the intense radiation environment near the Sun during the gravitational assist maneuver, and it would need to operate scientific instruments at velocities and distances never before attempted. Yet the potential scientific return would be enormous. Close-up observations could definitively resolve questions about Oumuamua's composition, structure, and surface properties that remain speculative based on distant telescopic observations. High-resolution images could reveal whether the object's unusual shape reflects its original formation or subsequent evolution during its interstellar journey. More importantly, a successful interception would demonstrate humanity's capability to reach interstellar objects, opening the possibility of studying visitors from other star systems before they disappear back into the cosmic deep. It would transform interstellar objects from fleeting curiosities into accessible targets for detailed scientific investigation. The technical challenges of such missions have inspired innovations in spacecraft design, propulsion systems, and autonomous navigation. Even if Project Lyra never launches, the engineering studies have advanced our capabilities for future deep space exploration. As our catalog of interstellar objects grows, researchers are beginning to search for patterns that might reveal their origins and evolutionary history. The 3 confirmed visitors, Oumuamua, Borisov, and ATLAS, show intriguing differences that hint at the diversity of these cosmic wanderers. Oumuamua's trajectory analysis suggests it approached our solar system from the direction of the star Vega, though the star's motion means it was in a very different location when the object began its journey. Borisov appeared to come from a different direction entirely, suggesting these objects don't originate from any single stellar neighborhood. The compositional differences are equally intriguing. While Borisov showed clear signs of water ice and familiar cometary compounds, spectroscopic analysis of the other objects has revealed different surface properties. This diversity suggests that interstellar objects sample a wide range of formation environments and evolutionary histories. Dr. Shokruz Kakarov's recent analysis of interstellar object trajectories has revealed another fascinating pattern. By tracing the orbits backward through galactic history, researchers can estimate when and where these objects were likely ejected from their parent systems. The results suggest that interstellar objects represent different epochs in galactic evolution. The oldest visitors, like 3I/ATLAS, appear to originate from stellar populations formed billions of years ago, when the galaxy was younger and star formation was more active. Younger objects like Oumuamua seem to come from more recent stellar generations. This temporal diversity means that interstellar objects carry information about galactic evolution spanning billions of years. The discovery of interstellar objects has profound implications for our understanding of planetary system formation throughout the galaxy. Current models suggest that most planetary systems go through chaotic early phases where gravitational interactions between forming planets eject substantial amounts of material into interstellar space. The efficiency of this process depends on the specific architecture of each system. Systems with massive gas giant planets are particularly effective at ejecting smaller objects, while systems dominated by rocky planets might retain more of their original material. The population of interstellar objects therefore reflects the diversity of planetary system architectures throughout the galaxy. This connection between interstellar objects and planetary formation has inspired new approaches to understanding exoplanet systems. By studying the properties and trajectories of interstellar visitors, astronomers can infer statistical properties of their parent systems. The composition of interstellar objects provides clues about the types of materials available during planet formation in other stellar systems. The implications extend to astrobiology as well. If interstellar objects can transport organic compounds between star systems, they might serve as vectors for spreading the chemical precursors of life throughout the galaxy. The discovery that objects like Oumuamua can survive million-year journeys through interstellar space suggests that even complex organic molecules might remain intact during such trips. Despite the growing acceptance of natural explanations for Oumuamua's properties, the question of artificial origin has had lasting impact on how astronomers approach unusual phenomena. Loeb's willingness to consider technological explanations, while controversial, has inspired more systematic approaches to searching for signs of extraterrestrial intelligence. The Galileo project, established partly in response to the Oumuamua controversy, represents a new paradigm in SETI research. Rather than focusing exclusively on radio signals, the project uses telescopes and sensors to search for physical artifacts that might indicate technological civilizations. This approach recognizes that any sufficiently advanced civilization would likely produce detectable artifacts during its expansion into space. Spacecraft, probes, debris from industrial activities, or even megascale engineering projects might be observable using existing astronomical techniques. The project has developed sophisticated algorithms for distinguishing between natural phenomena and potentially artificial objects. These systems analyze the orbital mechanics, surface properties, and behavioral characteristics of detected objects to identify those that warrant further investigation. While no confirmed technological artifacts have been discovered, the systematic search has already yielded insights into natural phenomena. Several objects initially flagged as potentially artificial have proven to be exotic but natural asteroids or comets with unusual properties. The search has also highlighted how difficult it would be to definitively identify alien technology, even if we encountered it. Any sufficiently advanced technology might appear natural to observers without detailed understanding of its operating principles. Conversely, natural phenomena operating under extreme conditions might mimic technological behavior. The Oumuamua controversy has sparked broader discussions about how science should approach extraordinary claims. Carl Sagan's famous dictum that extraordinary claims require extraordinary evidence is widely accepted, but the Oumuamua case has highlighted the complexity of applying this principle in practice. What constitutes an extraordinary claim? Loeb argues that the existence of technological civilizations elsewhere in the galaxy is not inherently extraordinary, given the billions of stars and potentially habitable planets. From this perspective, the discovery of alien technology would be surprising, but not unprecedented. Critics counter that invoking alien technology is premature when natural explanations remain plausible. They argue that the history of astronomy is filled with phenomena that initially seemed to require exotic explanations, but were ultimately understood through conventional physics. The debate reflects deeper philosophical questions about the nature of scientific reasoning. How should researchers balance skepticism against openness to novel ideas? When is it appropriate to consider radical explanations for unexplained phenomena? What role should prior probability assessments play in evaluating competing theories? These questions have practical implications for ongoing SETI research and the analysis of future interstellar objects. The scientific community's approach to extraordinary claims will influence how such phenomena are investigated and interpreted. Beyond its scientific implications, Oumuamua has had remarkable impact as an educational tool for communicating the nature of scientific inquiry. The object's journey from mysterious visitor to possibly understood phenomenon illustrates how science actually works, not as a series of definitive answers, but as an ongoing process of hypothesis formation, testing, and refinement. The controversy surrounding different explanations has shown students and the public that scientific disagreement is not a sign of failure, but an essential part of the discovery process. Scientists don't always agree on the interpretation of data, and this disagreement drives the deeper investigation needed to resolve complex questions. The interdisciplinary nature of Oumuamua research has also highlighted the interconnectedness of scientific fields. Understanding the object required insights from planetary science, astrochemistry, orbital mechanics, thermodynamics, and even high-energy physics. No single discipline contained all the necessary tools. Perhaps most importantly, the Oumuamua story demonstrates that the universe still holds surprises. Despite centuries of astronomical observation and sophisticated theoretical understanding, nature can still present us with phenomena that challenge existing frameworks. This keeps science vibrant and reminds us that our knowledge, however extensive, remains incomplete. Oumuamua's impact has extended far beyond the scientific community. The object has captured public imagination in ways that few astronomical discoveries achieve, inspiring books, documentaries, podcasts, and countless online discussions. Part of this appeal stems from the object's mysterious nature and the scientific controversy surrounding its origin. The possibility, however remote, that humanity might have encountered its first sign of alien technology resonates with fundamental questions about our place in the universe. The name itself, Oumuamua, meaning messenger from afar arriving first, captures the romantic appeal of the discovery. Here was a visitor from another star system, carrying information about distant worlds and cosmic processes we can barely imagine. The controversy between scientists has also made for compelling public drama. The clash between Loeb's bold hypothesis and the mainstream scientific community's skepticism has all the elements of an engaging narrative. A lone voice challenging established thinking, the gradual development of alternative explanations, and the ongoing uncertainty about which interpretation will ultimately prove correct. This public engagement with active scientific research is valuable for science communication. Rather than presenting science as a body of fixed knowledge, the Oumuamua story shows how scientific understanding develops in real time through debate, investigation, and the gradual accumulation of evidence. From an engineering perspective, the Oumuamua episode has provided valuable lessons about planetary defense and space situational awareness. The object was detected only after it had already passed closest approach to the Sun, highlighting gaps in our ability to detect incoming objects from interstellar space. This limitation has practical implications beyond scientific curiosity. While the probability is extremely low, there's no physical reason why a much larger interstellar object couldn't pass through our solar system. An object the size of a small asteroid could potentially pose a threat to Earth if its trajectory happened to intersect our planet's orbit. The limited warning time for Oumuamua, detected only as it was already departing the inner solar system, would be completely inadequate for mounting any kind of response to a hazardous object. This has motivated improvements in sky survey programs and the development of more sensitive detection systems. The discovery has also advanced our understanding of orbital mechanics under extreme conditions. Oumuamua's hyperbolic trajectory and non-gravitational acceleration presented orbital dynamicists with novel challenges in trajectory, determination, and prediction. The techniques developed for analyzing Oumuamua's complex motion have applications beyond interstellar objects. Similar methods can be used to study the subtle non-gravitational forces affecting spacecraft, comets, and asteroids within our solar system. As we look toward the future, the prospects for discovering and studying additional interstellar objects have never been better. The Vera C. Rubin Observatory will begin operations in 2025, providing unprecedented capability for detecting fast-moving objects against the stellar background. But detection is only the beginning. Future discoveries will benefit from the lessons learned during the Oumuamua episode. Observers now know what kinds of measurements are most crucial for characterizing interstellar objects. They understand the importance of rapid follow-up observations before objects fade from view. Advanced spectroscopic techniques will allow much more detailed analysis of composition and surface properties. Instruments designed specifically for studying transient phenomena will provide data quality that was impossible during Oumuamua's brief visibility. Perhaps most importantly, the space-based telescopes of the coming decades will enable observations that are impossible from Earth's surface. The James Webb Space Telescope, despite being optimized for different types of observations, has capabilities that could revolutionize interstellar object studies if properly applied. Future space missions specifically designed to intercept interstellar objects are also becoming more feasible. The European Space Agency's Comet Interceptor mission, while primarily intended for solar system comets, could potentially be redirected toward an interstellar target if one is discovered with sufficient advance warning. Even as scientific consensus appears to be forming around the hydrogen outgassing explanation for Oumuamua's properties, important questions remain unresolved. The object's extreme elongation still lacks a completely satisfactory explanation. The precise mechanisms by which cosmic ray bombardment creates and traps hydrogen in ice remain incompletely understood. These gaps in our understanding don't invalidate the hydrogen outgassing theory, but they do suggest that our picture of interstellar object evolution is still incomplete. Future laboratory experiments might help clarify the details of radiolysis in space environments. Computer simulations could explore how objects evolve during million-year journeys through varying interstellar conditions. The broader questions raised by Oumuamua's discovery will likely persist for decades. How common are interstellar objects? What range of compositions and properties do they exhibit? How do their characteristics relate to the properties of their parent planetary systems? Each new discovery will contribute pieces to this cosmic puzzle. But like many of the most interesting scientific questions, the investigation of interstellar objects will likely raise as many new questions as it answers. Perhaps the most profound impact of the Oumuamua discovery has been its effect on our cosmic perspective. The object has provided tangible evidence that our solar system exists within a vast galactic ecosystem where material flows freely between star systems. This realization fundamentally changes how we think about our place in the universe. We are not isolated inhabitants of a single stellar system, but participants in galactic-scale processes that operate over billions of years. The atoms in our bodies may have journeyed between star systems multiple times during the galaxy's history. The discovery also highlights the dynamic nature of cosmic evolution. Planetary systems are not static configurations, but evolving structures that exchange material with their galactic environment. This exchange might be crucial for understanding how life develops and spreads throughout the galaxy. From this perspective, every interstellar object represents a messenger carrying information about conditions in distant regions of space and time. By studying these cosmic wanderers, we gain insights into the diversity of planetary systems, the chemistry of interstellar space, and the long-term evolution of galactic structure. As we reach the conclusion of our journey through the Oumuamua mystery, it's important to recognize that this is not really an ending, but a milestone in an ongoing story. The hydrogen outgassing theory may provide the most satisfactory current explanation for the object's properties, but science is a process of continuous refinement and revision. Future discoveries may confirm this explanation or require fundamental modifications. New theoretical insights might reveal aspects of interstellar object evolution that we haven't yet considered. Advanced space missions could provide data that transforms our understanding entirely. What remains constant is the spirit of inquiry that drove the investigation of Oumuamua from the beginning. When faced with phenomena that don't fit existing categories, scientists respond with creativity, collaboration, and persistent investigation. They propose hypotheses, test predictions, and gradually build more complete pictures of natural phenomena. The Oumuamua episode has demonstrated this process at its best. Researchers from multiple disciplines and institutions contributed insights that gradually illuminated different aspects of the mystery. Theoretical models were proposed, criticized, refined, and sometimes abandoned as new evidence emerged. This collaborative, iterative process represents science at its most effective. No single researcher or institution could have solved the Oumuamua puzzle alone. It required the combined efforts of observers, theorists, experimentalists, and modelers working together across traditional disciplinary boundaries. Whatever its ultimate nature proves to be, Oumuamua has already secured its place as one of the most significant astronomical discoveries of the early 21st century. The object has opened an entirely new field of research, inspired innovative approaches to searching for extraterrestrial intelligence, and demonstrated the power of international scientific collaboration. Perhaps most importantly, Oumuamua has reminded us that the universe still holds profound mysteries. Despite our sophisticated understanding of physics and astronomy, nature can still surprise us with phenomena that challenge our theoretical frameworks and expand our conception of what's possible. The object has also highlighted the importance of maintaining diverse perspectives in scientific research. The controversy between conventional and exotic explanations, while sometimes uncomfortable, has ultimately strengthened our understanding by forcing more rigorous analysis of all possibilities. As future surveys detect dozens or hundreds of additional interstellar objects, each will be compared to our first visitor. Oumuamua will remain the standard against which all other interstellar objects are measured, the discovery that proved such cosmic wanderers exist and can be studied. The story of Oumuamua is ultimately a story about human curiosity and our relentless drive to understand the cosmos. When presented with an object that defied explanation, the global scientific community responded with creativity, determination, and collaborative spirit. The investigation required pushing observational techniques to their limits, developing new theoretical frameworks, and considering possibilities that seemed almost too extraordinary to contemplate. It demanded interdisciplinary collaboration on an unprecedented scale, and the willingness to challenge established assumptions. The hydrogen outgassing theory that has emerged as the leading explanation represents a triumph of scientific methodology. It explains the observed phenomena using well-understood physical processes, makes testable predictions, and fits within our broader understanding of cosmic evolution. Yet the theory also reminds us how much we still don't know about the universe. The idea that cosmic ray bombardment can fundamentally transform objects over million-year timescales was not widely appreciated before Oumuamua's discovery. The realization has opened new avenues of research into interstellar chemistry and the evolution of small bodies in space. As Oumuamua continues its journey toward the constellation Pegasus, now beyond the orbit of Neptune and invisible to even our most powerful telescopes, it carries with it the secrets of its true nature. We may never know with absolute certainty whether our theories are correct, but in the attempt to understand this cosmic messenger, we have learned something profound about both the universe and ourselves. The cosmos is vast, ancient, and filled with processes operating on scales of space and time that dwarf human experience. Yet through careful observation, creative thinking, and collaborative effort, we can begin to comprehend even the most exotic phenomena. Oumuamua has shown us that the universe is stranger and more wonderful than we imagined, but not beyond our ability to understand. In the end, perhaps that is Oumuamua's greatest gift to humanity, the reminder that we live in a universe of endless mystery and discovery, where every answer reveals new questions, and every discovery opens new frontiers for exploration. The cosmic messenger from afar has delivered its message. The universe is vast, complex, and full of wonders waiting to be discovered by those bold enough to seek them. But our story doesn't end with Oumuamua. Just as scientists were beginning to feel confident about the hydrogen outgassing explanation, the cosmos delivered another surprise that would fundamentally alter our understanding of interstellar visitors. On July 1st, 2025, precisely 8 years after Oumuamua's discovery, the Atlas telescope system in Chile detected something unprecedented moving through our solar system. Initially designated with the cryptic code A113Z, this new object would soon be officially named 3I-ATLAS, marking it as the third confirmed interstellar visitor to our solar system. But unlike its predecessors, 3I-ATLAS carried with it revelations that would challenge everything we thought we knew about these cosmic wanderers. The discovery itself was remarkable for reasons that extend far beyond the object's interstellar origin. 3I-ATLAS was detected not as it departed our solar system, like Oumuamua, but as it approached the Sun. This timing difference would prove crucial, offering astronomers an unprecedented opportunity to study an interstellar object during its most active phase. Within hours of its detection, something extraordinary became apparent. Unlike Oumuamua's mysterious lack of visible activity, 3I-ATLAS was behaving exactly like a textbook comet. As solar heating warmed its nucleus, the object began ejecting gas and dust, creating a brilliant coma that grew from 13,000 kilometers in diameter to nearly 19,000 kilometers within just 11 days. Dr. David Jewett at UCLA, one of the astronomers who confirmed the object's cometary nature, described the discovery with barely contained excitement. Here was an interstellar object that wasn't hiding its secrets behind puzzling behavior. It was displaying its nature openly, offering scientists the detailed observations that had been impossible with Oumuamua. But perhaps most significantly, 3I-ATLAS was fast, incredibly fast. Moving at over 130,000 miles per hour, it became the fastest interstellar object ever recorded passing through our solar system. This velocity carried profound implications that would revolutionize our understanding of interstellar object populations and galactic dynamics. The speed of 3I-ATLAS wasn't just a curious detail, it was a cosmic clock that revealed the object's extraordinary history. Dr. Matthew Hopkins at the University of Oxford, whose doctoral research had focused on predicting the properties of interstellar objects, found himself in the remarkable position of having a real specimen appear just 5 days after he completed his thesis. Hopkins and his colleagues had developed sophisticated models connecting an object's velocity to its age and origin. The principle is elegantly simple. As objects travel through the galaxy, they experience gravitational encounters with stars and stellar nurseries that gradually accelerate them. The faster an object moves, the longer it has been wandering through space. Applied to 3i/ATLAS, this velocity-age relationship yielded a staggering conclusion. The comet has a 67% probability of being more than 7.6 billion years old, making it ancient beyond our solar system's entire existence. When our sun was still a collapsing cloud of gas and dust, 3i/ATLAS was already wandering the galaxy as a fully formed comet. This age estimate represents more than just an impressive number. It suggests that 3i/ATLAS predates our solar system by over 3 billion years, carrying within its nucleus chemical signatures from an era when the galaxy was younger, when star formation was more active, when the cosmic environment was fundamentally different from today. The implications are profound. 3i/ATLAS isn't just a visitor from another star system, it's a time traveler from an ancient epoch of galactic evolution. Its composition, structure, and behavior provide a direct link to conditions that existed when the Milky Way was in its cosmic adolescence. Analysis of 3i/ATLAS's trajectory revealed another layer of its remarkable story. The object's motion through space doesn't match the orderly rotation of stars in our galaxy's thin disk, where most star formation occurs today. Instead, its orbital characteristics place it firmly in what astronomers call the thick disk population, a realm of older stars with different chemical compositions and more chaotic orbital patterns. Dr. Shokruz Kakarov's detailed trajectory analysis, conducted in collaboration with Harvard's Avi Loeb, revealed that 3i/ATLAS is moving away from the galactic center with unusual vertical velocity components. This motion pattern suggests the comet belongs to an ancient stellar population that formed when the galaxy's structure was significantly different from its current configuration. The thick disk represents a fossil record of early galactic evolution, containing stars and associated planetary systems that formed during more turbulent epochs. Objects ejected from planetary systems in this population carry chemical signatures reflecting the different cosmic conditions of their birth environments, potentially including lower concentrations of heavy elements and different isotopic ratios. This connection between 3i/ATLAS and ancient galactic populations provides astronomers with an unprecedented opportunity to study material from the early Milky Way. Rather than inferring the properties of ancient stellar systems from distant observations, scientists can now examine actual samples of matter ejected from those systems billions of years ago. As telescopes around the world focused on 3i/ATLAS, detailed spectroscopic analysis began revealing the object's chemical composition. The results were both familiar and surprising. Like 2I/Borisov, the comet shows clear signs of water ice and organic compounds, but unlike typical solar system comets, its dust displays unusual properties that hint at its exotic origins. The Hubble Space Telescope's high-resolution observations, captured when 3i/ATLAS was 277 million miles from Earth, revealed a teardrop-shaped dust cocoon streaming from the comet's nucleus. This dust appears reddish in color, similar to organic compounds that have been irradiated by cosmic rays over extended periods. But spectroscopic analysis revealed intriguing differences from solar system comets. The relative abundances of certain molecular species suggest formation conditions that don't match our local environment. These subtle but significant variations provide clues about the chemical evolution of the comet's parent stellar system and the galactic environment in which it formed. Perhaps most intriguingly, the comet's activity patterns differ subtly from expectations based on solar system comets. While it displays the expected brightening as it approaches the sun, the rate of gas and dust production suggests internal structure or composition differences that reflect its unique evolutionary history. Dr. Colin Snodgrass at the University of Edinburgh, who has been tracking the object's development, notes that these compositional differences, while subtle, could provide crucial insights into planetary formation processes in other stellar systems. Each measurement adds another piece to the puzzle of how planetary systems evolve in different galactic environments. One of the most challenging aspects of studying 3I/ATLAS has been determining its actual size. Initial estimates suggested a nucleus diameter of about 20 kilometers, making it substantially larger than both Oumuamua and Borisov. But as more sophisticated observations became available, this estimate underwent dramatic revisions. Data from the newly operational Vera C. Rubin Observatory in Chile reduced the size estimate to approximately 10 kilometers. Then, detailed analysis of Hubble Space Telescope observations further refined the measurement to just 5.6 kilometers in diameter. Some models suggest the nucleus could be even smaller, potentially as little as 320 meters across. This uncertainty reflects the fundamental challenges of studying objects at interstellar distances. The brightness we observe comes from both reflected sunlight from the nucleus and scattered light from the surrounding dust coma. Separating these components to determine the true size of the solid nucleus requires sophisticated modeling and high-quality observational data. But the size uncertainty also highlights something profound about interstellar objects. Unlike solar system comets, which we can study over multiple orbital periods, interstellar visitors offer only a single observational opportunity. Every measurement must be made during their brief passage through the inner solar system. The potential size range for 3I/ATLAS, from hundreds of meters to several kilometers, encompasses objects that could have very different formation histories and evolutionary pathways. Understanding the true dimensions will be crucial for interpreting the comet's behavior and origins. The velocity of 3I/ATLAS, over 130,000 miles per hour relative to our solar system, represents more than just impressive speed. It provides a direct measurement of the kinetic energy accumulated during billions of years of galactic wandering. This energy represents countless gravitational encounters with stars, molecular clouds, and other massive objects during the comet's epic journey. Computer simulations suggest that achieving such extreme velocities requires not just time, but specific types of gravitational encounters. Close passes by massive stars or passage through dense stellar regions can impart the energy needed to accelerate objects to these extraordinary speeds. Each encounter leaves its mark, not just in increased velocity, but potentially in the object's physical structure and composition. The fact that 3I/ATLAS has survived this high-speed journey intact suggests remarkable structural integrity. Unlike the fragile, loosely bound rubble piles that characterize many solar system comets, interstellar travelers must possess sufficient internal strength to withstand the stresses of prolonged high-speed travel through varying gravitational environments. This durability requirement may explain some of the unusual properties observed in interstellar objects. The extreme conditions of interstellar travel could select for objects with specific structural characteristics, creating a population that differs systematically from the comets and asteroids we observe in our local environment. The discovery and initial characterization of 3I/ATLAS marked a watershed moment for interstellar object research, largely due to the capabilities of new observational facilities. The Vera C. Rubin Observatory, which achieved first light in 2024, demonstrated its revolutionary potential by contributing crucial early observations of the comet's development. The observatory's unprecedented combination of large aperture, wide field of view, and rapid cadence observations allows it to monitor the entire visible sky every few nights. This capability proved crucial for tracking 3I/ATLAS's rapidly evolving coma and determining its physical properties during the critical early weeks after discovery. But Rubin Observatory represents more than just improved sensitivity. Its systematic survey approach means that future interstellar objects will likely be detected much earlier in their approaches to the Sun. Rather than discovering visitors as they depart, like Oumuamua, future detections may provide months or even years of advance warning. Dr. Daryl Seligman, the Michigan State University researcher who led the rapid scientific response to 3I/ATLAS, emphasizes how this early warning capability could transform interstellar object science. Extended observation periods would allow detailed spectroscopic studies, monitoring of activity evolution, and potentially even spacecraft missions to intercept these cosmic visitors. The observatory's impact extends beyond individual discoveries. By detecting dozens of interstellar objects annually, it will provide the statistical samples needed to understand population characteristics, origin distributions, and the relationship between interstellar visitors and galactic evolution. Perhaps the most profound implication of 3I/ATLAS's ancient age concerns what it might tell us about the early chemical evolution of our galaxy. When this comet formed over 7 billion years ago, the cosmic environment was fundamentally different from today's conditions. Star formation was more active, creating massive stars that lived fast and died young in spectacular supernovae. These stellar explosions enriched the interstellar medium with heavy elements, gradually changing the chemical composition of gas clouds from which new stars and planets formed. 3I/ATLAS condensed from material in this ancient environment, incorporating chemical signatures that reflect the galactic conditions of its birth epoch. By analyzing its composition, astronomers can potentially probe the chemical state of the galaxy billions of years ago. The isotopic ratios of elements within the comet could reveal the nucleosynthetic processes that were dominant when it formed. Different types of supernovae produce distinct isotopic signatures, and the relative contributions of these processes have changed over galactic time. Even more intriguingly, the organic compounds detected in 3I/ATLAS may preserve molecular fossils from the early galaxy. These complex molecules could provide insights into the prebiotic chemistry that was occurring in planetary systems billions of years before life emerged on Earth. The discovery of 3I/ATLAS has profound implications for our understanding of galactic archaeology, the study of how galaxies evolve over cosmic time. Traditional approaches to galactic archaeology rely on analyzing the light from distant stars to infer their ages, compositions, and formation histories. Interstellar objects offer a complementary approach, direct sampling of material ejected from stellar systems at different epochs in galactic evolution. Each visitor carries within its structure a record of the conditions that existed when and where it formed. The age distribution of interstellar objects could reveal the history of planetary system formation throughout the galaxy. Objects ejected during different epochs would carry signatures of the stellar populations and chemical conditions that existed at those times. 3I/ATLAS, as a representative of the ancient thick disk population, provides our first direct sample of material from the early galactic environment. But future discoveries may reveal objects from even earlier epochs, potentially including the galaxy's initial star-forming burst. The chemical and physical diversity of these objects could map the spatial and temporal variation in planetary formation processes throughout galactic history. This information is impossible to obtain through any other observational technique. The discovery of 3I/ATLAS, arriving from the direction opposite to the Sun, has sparked renewed discussion about interstellar interception missions. Unlike Oumuamua, which was detected after its closest solar approach, 3I/ATLAS was discovered while approaching the Sun, providing potentially sufficient time for a rapid response mission. Atsuhiro Yaganuma, an undergraduate researcher working with Daryl Seligman, has been investigating the feasibility of launching a spacecraft to intercept 3I ATLAS during its closest approach to Earth in December 2025. While the technical challenges are enormous, the scientific return could be unprecedented. Such a mission would require rapid mobilization of resources and cutting-edge propulsion technology. The spacecraft would need to achieve extreme velocities to match 3I/ATLAS's trajectory, potentially using multiple gravitational assists and advanced propulsion systems. But the potential discoveries justify the effort. Close-up observations could resolve questions about the comet's internal structure, surface composition, and formation history that remain speculative based on distant telescopic observations. Direct sampling of ancient interstellar material could revolutionize our understanding of galactic evolution. The European Space Agency's Comet Interceptor mission, currently in development, represents a more realistic approach to interstellar object encounters. This mission will wait at the L2 Lagrange point, ready to redirect toward any promising interstellar visitor detected with sufficient advance warning. Beyond its individual significance, 3I/ATLAS represents a crucial data point in the growing statistical sample of interstellar objects. With 3 confirmed visitors, Oumuamua, Borisov, and ATLAS, astronomers can begin to discern population characteristics and test theoretical predictions. The diversity among these objects is striking. Oumuamua showed no detectable activity and unusual acceleration. Borisov behaved like a typical solar system comet. 3I/ATLAS displays vigorous activity and extreme age. This variety suggests that interstellar space contains a rich population of objects with diverse properties and evolutionary histories. The age distribution is particularly intriguing. While Oumuamua appears to be about 1 billion years old, and Borisov approximately 1.7 billion years old, 3I/ATLAS may be over 7 billion years old. This spread suggests that objects are ejected from planetary systems throughout galactic history, not just during brief periods of intense activity. The trajectory analysis reveals another pattern. Each object arrived from a different direction, suggesting they don't originate from any single stellar neighborhood. Instead, they appear to represent a distributed population of wanderers that permeates interstellar space. As the Vera Rubin Observatory begins detecting dozens of interstellar objects annually, these statistical patterns will become more robust. The resulting data will test theoretical models of planetary system evolution and provide constraints on the formation and ejection processes that populate interstellar space. The spectroscopic analysis of 3I/ATLAS is revealing chemical signatures that reflect its ancient origins and exotic formation environment. Unlike solar system comets, which formed from material in our local stellar nebula, 3I/ATLAS condensed from gas and dust in a vastly different stellar system billions of years ago. The relative abundances of various molecular species provide clues about the conditions in its parent system. The ratios of different isotopes can reveal the nucleosynthetic history of the stellar environment where the comet formed. These measurements provide direct samples of material from the ancient galaxy. Early spectroscopic observations have detected water vapor, carbon monoxide, and various organic compounds, similar to solar system comets, but with subtle differences that reflect the comet's exotic origins. The isotopic ratios of carbon, nitrogen, and oxygen could reveal whether the parent stellar system had different chemical enrichment than our Sun. Perhaps most intriguingly, the organic compounds in 3I/ATLAS may preserve molecular complexity that developed over billions of years of cosmic evolution. These molecules have been subjected to cosmic ray bombardment and chemical processing during the comet's epic journey, potentially creating compounds that don't exist in our solar system. The dust particles ejected from the comet carry additional chemical information. High-resolution analysis of this dust could reveal mineral compositions reflecting formation temperatures and pressures in the ancient stellar nebula where 3I-ATLAS originated. One of the most remarkable aspects of 3I-ATLAS is simply that it exists at all, surviving a 7 billion year journey through interstellar space while maintaining sufficient volatile material to display vigorous cometary activity challenges our understanding of comet evolution and durability. Solar system comets typically lose most of their volatile material within a few thousand years of regular solar heating, yet 3I-ATLAS, after billions of years in space, still contains enough ice to create a dramatic coma spanning tens of thousands of kilometers. This longevity suggests either that interstellar comets possess fundamentally different structures than their solar system counterparts, or that the conditions of interstellar space are more benign for comet preservation than previously thought. The cosmic ray bombardment that occurs during interstellar travel should gradually alter the comet's chemistry, potentially creating the trapped hydrogen that may explain Oumuamua's mysterious acceleration. But 3I-ATLAS shows no signs of such non-gravitational forces, suggesting its internal structure or composition differs from what the hydrogen outgassing model would predict. The thermal environment of deep space, while cold, isn't uniform. Passage through molecular clouds, stellar radiation fields, and regions of varying cosmic ray intensity would subject the comet to different processing environments during its journey. Understanding how 3I-ATLAS survived its epic journey intact will be crucial for interpreting observations of future interstellar visitors and for understanding the population of objects that successfully navigate the hazards of interstellar space. One of the most significant aspects of 3I-ATLAS's behavior is what it doesn't do. Unlike Oumuamua, which displayed mysterious non-gravitational acceleration, 3I-ATLAS follows a predictable gravitational trajectory with no detectable deviations. This difference has profound implications for understanding interstellar object physics. If the hydrogen outgassing theory correctly explains Oumuamua's acceleration, then 3I-ATLAS should show similar behavior. The comet has spent even longer in interstellar space, experiencing more cosmic ray bombardment that should create even larger quantities of trapped hydrogen gas. Yet detailed tracking of 3I-ATLAS's orbit reveals no signs of the subtle acceleration that characterized Oumuamua. The comet follows a precise hyperbolic trajectory that matches gravitational predictions exactly. This discrepancy could suggest several possibilities. Perhaps the hydrogen outgassing mechanism depends on specific structural or compositional properties that 3I-ATLAS doesn't possess. Maybe the process requires particular thermal conditions that occur only in certain types of interstellar objects. Alternatively, the difference might reflect the object's different evolutionary histories. 3I-ATLAS shows vigorous outgassing of conventional material, which might mask or prevent the subtle effects of hydrogen emission. The active coma and tail could overwhelm any non-gravitational forces from trapped hydrogen. This comparison between interstellar objects provides a natural experiment for testing theories about their behavior and evolution. As more visitors are discovered, the pattern of which objects show non-gravitational acceleration could reveal the physical mechanisms responsible for these effects. The extreme age of 3I-ATLAS raises profound questions about planetary system evolution in the early galaxy. When this comet formed over 7 billion years ago, The chemical composition of star-forming gas clouds was significantly different from today's conditions. Early stellar systems contained lower concentrations of heavy elements, affecting the types of planets that could form and the compositions of comets and asteroids. The dust grains and organic molecules available for comet construction would have reflected these different chemical conditions. Yet 3I/ATLAS appears remarkably similar to more recent comets in its basic composition and behavior. This similarity suggests that the fundamental processes of comet formation, the accretion of ice, dust, and organic materials in the cold outer regions of stellar systems, operate consistently across different chemical environments and cosmic epochs. The comet's survival and preservation of volatile materials also implies that its parent stellar system successfully ejected it into interstellar space before internal heating or stellar evolution could destroy its icy components. This ejection must have occurred relatively early in the system's history. The mechanism that launched 3I/ATLAS into interstellar space likely involved gravitational interactions with massive planets during the chaotic early phases of planetary system formation. Understanding this ejection process provides insights into the architecture and evolution of the ancient stellar system where the comet originated. The study of 3I/ATLAS has benefited from observational capabilities that simply didn't exist during Oumuamua's passage. The Hubble Space Telescope's detailed images reveal structure in the comet's coma that provides direct information about the nucleus's activity patterns and composition. Ground-based telescopes equipped with advanced adaptive optics systems have captured high-resolution spectra showing the detailed molecular composition of the comet's outgassing material. These observations provide chemical fingerprints that can be compared with theoretical models of comet formation and evolution. The rapid coordination of global observing campaigns has maximized the scientific return from 3I/ATLAS's visit. Within hours of the discovery announcement, telescopes on multiple continents were tracking the object, gathering complementary data that builds a comprehensive picture of its properties. This coordinated response demonstrates how the astronomical community has evolved since Oumuamua's surprise visit. Established protocols now ensure that rare interstellar visitors receive immediate intensive study using the best available instruments. Future observations will continue as 3I/ATLAS approaches its October perihelion. The increasing solar heating may trigger outburst events or reveal additional activity patterns that provide further insights into the comet's internal structure and composition. Perhaps the most profound implication of 3I/ATLAS's discovery concerns our connection to deep galactic time. This ancient wanderer provides a direct physical link to epochs of cosmic history that we can study in no other way. When 3I/ATLAS formed, the universe was less than half its current age. The first complex multicellular life was just beginning to emerge on Earth. The galactic environment was more active, with higher rates of star formation and more frequent supernova explosions, enriching the interstellar medium with heavy elements. The comet carries within its nucleus chemical signatures from this ancient epoch. Every molecule of water ice, every grain of dust, every organic compound formed under conditions that no longer exist in our local galactic neighborhood. By studying 3I/ATLAS, astronomers can probe the chemical and physical conditions that existed when our galaxy was young. This information complements traditional approaches to understanding galactic evolution, which rely on analyzing light from distant stars and galaxies. The comet also represents a harbinger of discoveries to come. As survey capabilities improve and more interstellar objects are detected, we can expect to find visitors from even earlier cosmic epochs, potentially including material from the galaxy's first generation of stars. The detection and characterization of 3I/ATLAS represents a triumph of modern astronomical technology and international collaboration. The discovery by the ATLAS survey system demonstrates how automated telescopes can continuously monitor the entire sky, detecting rare and unexpected phenomena that would be impossible to find through traditional observing approaches. The rapid confirmation of the object's interstellar nature required precise astrometric measurements from multiple observatories around the world. Within 24 hours of discovery, enough data had been collected to conclusively demonstrate that 3I/ATLAS was not bound to our solar system. The subsequent observational campaign involved dozens of telescopes spanning multiple continents and space-based facilities. This coordinated effort maximized the scientific return during the critical early phases when the comet's properties could be determined. Advanced data analysis techniques, including machine learning algorithms and automated image processing, enabled rapid extraction of scientific information from the flood of observational data. These tools allow astronomers to characterize interstellar objects much more efficiently than was possible during Oumuamua's visit. The technical infrastructure that made 3I/ATLAS's discovery and study possible represents decades of investment in astronomical capabilities. The payoff is a detailed understanding of an ancient cosmic visitor that would have been impossible to achieve just a few years ago. The discovery and study of 3I/ATLAS marks the beginning of what might be called the age of interstellar astronomy, with advanced survey capabilities coming online and established protocols for rapid follow-up observations. The detection of interstellar objects is transitioning from rare, headline-grabbing events to routine scientific observations. The Vera Rubin Observatory's legacy survey of space and time will likely detect dozens of interstellar visitors annually, providing the statistical samples needed to understand population characteristics and test theoretical models. Each new discovery will contribute to our growing understanding of these cosmic wanderers. Future space missions, including ESA's Comet Interceptor, may achieve close-up encounters with interstellar objects, gathering data impossible to obtain through remote observations. These missions could analyze surface composition, internal structure, and detailed chemistry of material from other stellar systems. The James Webb Space Telescope's unprecedented infrared capabilities could revolutionize interstellar object spectroscopy, potentially detecting complex organic molecules and revealing detailed chemical compositions. Its sensitivity could enable observations of much fainter objects than currently possible. Advanced laboratory techniques for analyzing cosmic dust and meteorite samples may eventually be applied to particles collected from interstellar visitors. Such direct sampling would provide ultimate ground truth for theoretical models of interstellar object composition and evolution. The study of interstellar objects like 3I/ATLAS is fundamentally changing how we think about our solar system's place in the galaxy. Rather than an isolated island of matter orbiting a single star, we now recognize our cosmic neighborhood as part of a vast galactic ecosystem where material flows freely between stellar systems. This perspective shift has implications beyond academic astronomy. Understanding the flux of interstellar material through our solar system could be crucial for assessing long-term risks and opportunities. While the probability of hazardous impacts is extremely low, the possibility cannot be completely ignored. The chemical diversity of interstellar objects also raises intriguing possibilities for astrobiology. If life-bearing material can survive interstellar journeys, then biological information might spread throughout the galaxy through natural processes. Each interstellar visitor represents a potential sample from environments where life might have emerged. The technological signatures that could be preserved in artificial interstellar objects continue to motivate SETI research. While all confirmed visitors to date appear natural, the possibility of eventual contact with technological artifacts remains open. Despite the wealth of information gathered about 3I/ATLAS, fundamental questions remain unanswered. The precise mechanisms that preserve volatile materials during billion-year interstellar journeys are still poorly understood. The relationship between object age, composition, and survival probability requires more data to resolve. The absence of non-gravitational acceleration in 3I/ATLAS, despite its ancient age and presumed cosmic ray exposure, challenges theories proposed to explain Oumuamua's mysterious behavior. Understanding why some interstellar objects show these effects while others don't will be crucial for developing comprehensive models. The formation mechanisms that create objects with such extreme age and unusual properties remain speculative. How do planetary systems in the early galaxy produce comets that can survive for billions of years? What ejection processes send them into the interstellar medium? Future discoveries will undoubtedly reveal new puzzles and challenge existing theories. The universe has already surprised us with Oumuamua's exotic behavior and 3I/ATLAS's ancient age. What other mysteries await discovery in the cosmic wanderers still approaching our solar system? The impact of interstellar object discoveries extends far beyond the objects themselves. These cosmic visitors have catalyzed developments in observational technology, theoretical modeling, and international scientific collaboration that benefit many areas of astronomy. The rapid response protocols developed for interstellar object characterization are being applied to other transient astronomical phenomena. The data analysis techniques and observational strategies pioneered for these studies are advancing the broader field of time domain astronomy. The international cooperation required for effective interstellar object science demonstrates how the global astronomical community can mobilize resources for studying rare and unexpected phenomena. These collaborative approaches serve as models for addressing other scientific challenges requiring rapid, coordinated responses. The public fascination with interstellar visitors has also created opportunities for science communication and education. The mystery and exotic nature of these objects capture imagination while providing excellent examples of how scientific understanding develops through observation, hypothesis testing, and peer review. As we conclude our extended journey through the mysteries of Oumuamua and the revelations of 3I/ATLAS, the profound implications of these discoveries continue to resonate. We have learned that our solar system exists within a galaxy teeming with wandering objects that carry information about cosmic environments and evolutionary processes spanning billions of years. These ancient messengers challenge our understanding of planetary system formation, galactic evolution, and the chemical processing that occurs during epic journeys through interstellar space. Each visitor represents a unique experiment in cosmic evolution, shaped by conditions and processes that exist nowhere in our local environment. The hydrogen outgassing theory that emerged to explain Oumuamua's mysterious behavior may prove correct, but the absence of similar effects in 3I/ATLAS suggests that interstellar object physics is more complex than any single mechanism can explain. The diversity of these cosmic visitors appears to exceed our current theoretical frameworks, yet perhaps the most important lesson from these discoveries is how much more there is to learn. The universe continues to surprise us with phenomena that challenge existing models and expand our conception of what's possible. Every answer reveals new questions. Every discovery opens new frontiers for exploration. The ancient comet 3I/ATLAS, carrying within its nucleus the chemical memories of a younger galaxy, reminds us that we are temporary inhabitants of a cosmos vast in both space and time. We live in an era when technology finally allows us to study these cosmic time travelers, to read the chemical stories written in ice and dust over billions of years of galactic evolution. Somewhere in the darkness beyond Neptune, Oumuamua continues its journey toward the constellation Pegasus, carrying with it the secrets of its true nature. Meanwhile, 3I/ATLAS approaches its rendezvous with the Sun, offering astronomers unprecedented opportunities to study material from the ancient galaxy. Both objects, in their own ways, have transformed our understanding of the cosmos. They have shown us that the universe is far stranger, more dynamic, and more interconnected than we previously imagined. And they have reminded us that the greatest discoveries often come not from confirming what we expect, but from embracing the unexpected. The age of interstellar astronomy has begun. As survey telescopes scan the skies and detection capabilities improve, more cosmic wanderers will reveal themselves, each carrying its own stories from distant places and ancient times. The universe, it seems, has many more messages to deliver to those patient enough to listen and bold enough to seek understanding in the vast darkness between the stars. But as we approached the end of 2024, another revelation emerged that would further complicate our understanding of mysterious cosmic visitors. Just weeks before 3I/ATLAS approached its solar encounter, NASA researchers announced a discovery that would fundamentally alter the context in which we interpret Oumuamua's strange behavior. Dr. Daryl Seligman, the same researcher who had proposed the hydrogen outgassing theory for Oumuamua and led the rapid scientific response to 3I/ATLAS, was about to unveil findings that would create an entirely new category of celestial objects. Working with Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory, Seligman had been systematically analyzing objects within our solar system that exhibited puzzling characteristics. The investigation had begun with an object designated 2003 RM, discovered over 2 decades earlier. This seemingly ordinary asteroid displayed subtle but persistent non-gravitational acceleration, similar to what would later be observed in Oumuamua. But unlike interstellar visitors, 2003 RM was clearly a member of our solar system, orbiting the Sun in a conventional elliptical path. The mystery deepened as more objects with similar properties were identified. By 2023, 7 such objects had been cataloged, celestial bodies that looked like asteroids but behaved like comets, showing evidence of outgassing forces despite having no visible coma or tail. The astronomical community officially designated these enigmatic objects as dark comets, creating an entirely new classification category. The December 2024 announcement doubled this population overnight. Seligman and his team had identified 7 additional dark comets, bringing the total to 14 confirmed examples. But more significantly, the larger sample size revealed something unexpected. Dark comets come in 2 distinct varieties, each with different characteristics that hint at different origins and evolutionary pathways. The analysis of 14 dark comets revealed a striking pattern that nobody had anticipated. Rather than forming a single population of similar objects, these mysterious bodies fell into 2 distinct categories with markedly different properties. The first group, which researchers designated as outer dark comets, shared characteristics with Jupiter family comets. They followed highly eccentric, elliptical orbits that carried them to the outer reaches of the solar system before returning to the inner planets. These objects were relatively large, measuring hundreds of meters or more across, suggesting substantial internal mass and structure. The second population, the inner dark comets, presented entirely different characteristics. These objects inhabited the inner solar system, following nearly circular orbits that kept them relatively close to the Sun. They were much smaller than their outer counterparts, typically measuring tens of meters or less in diameter. Their orbital properties suggested they had been shaped by different formation processes or evolutionary histories. This bifurcation raised profound questions about the origins and nature of dark comets. Were they remnants of different formation processes? Did they represent material from different regions of the early solar system? Or were they examples of how similar objects could evolve along different pathways under varying environmental conditions? Dr. Seligman noted that the discovery of 2 distinct populations provided crucial insights into solar system dynamics. The inner dark comets, with their circular orbits and small sizes, might represent fragments of larger bodies that had been broken apart by collisional processes or gravitational disruption. The outer dark comets, with their eccentric orbits and larger sizes, appeared more similar to conventional comets that had somehow lost their ability to produce visible tails. The discovery of multiple dark comet populations within our solar system provided crucial context for interpreting Oumuamua's mysterious properties. If objects that looked like asteroids but behaved like comets were relatively common in our local environment, then Oumuamua's strange behavior might not be as unprecedented as initially believed, but the connection raised as many questions as it answered. Oumuamua was clearly from interstellar space, while dark comets were solar system natives, yet both categories displayed similar non-gravitational accelerations without visible cometary activity. Were these phenomena related, or were they examples of convergent evolution producing similar observational signatures through different physical mechanisms? The size comparison proved particularly intriguing. Oumuamua, at several hundred meters in length, fell into the same size range as the outer dark comets. Its elongated shape and tumbling rotation were also consistent with objects that had experienced substantial evolutionary processing. Perhaps Oumuamua represented an extreme example of the same processes that created dark comets in our solar system, yet significant differences remained. Oumuamua's hyperbolic trajectory and interstellar origin clearly distinguished it from solar system dark comets. Its extreme elongation exceeded anything observed among dark comets, suggesting either different formation conditions or more extreme evolutionary processing during its interstellar journey. The chemical composition question remained unresolved. Dark comets presumably contained the familiar mixture of water ice, carbon compounds, and rocky material typical of solar system small bodies. Oumuamua's composition remained uncertain, with various theories proposing everything from conventional comet material to exotic hydrogen ice to artificial constructions. The discovery of dark comets had an unexpected consequence. It reignited debate about Oumuamua's possible artificial origin. Dr. Avi Loeb, the Harvard astrophysicist who had long advocated for considering technological explanations, seized upon the dark comet findings as additional evidence supporting his hypothesis. Loeb's argument was both elegant and provocative. If dark comets showed non-gravitational acceleration, similar to Oumuamua's behavior, and if some of these objects might actually be human space debris rather than natural bodies, then the possibility that Oumuamua itself was artificial could not be dismissed. The precedent existed. In 2020, an object designated 2020 SO was discovered, showing non-gravitational acceleration consistent with solar radiation pressure. Initially classified as a potential dark comet or asteroid, 2020 SO was later identified as the upper stage of a Surveyor 2 rocket launched by NASA in 1966. The object had been orbiting in space for over 50 years before returning to Earth's vicinity. This identification proved that human-made objects could indeed show the kind of mysterious acceleration that characterized both Oumuamua and dark comets. It also demonstrated how difficult it could be to distinguish between natural and artificial objects based on observational data alone. Loeb argued that if our own space age, barely 70 years old, could produce objects that mimicked natural comets, then a more advanced civilization might create artifacts that would be even harder to distinguish from natural phenomena. The fact that some dark comets might actually be space debris suggested that the category included both natural and artificial objects. This reasoning led Loeb to propose that systematic searches for dark comets might inadvertently discover technological artifacts from other civilizations. Objects showing non-gravitational acceleration without visible outgassing could include not only natural bodies with unusual compositions, but also defunct spacecraft, discarded equipment, or even active technological systems. The dark comet revelations gained additional significance from an unexpected source. Japan's Hayabusa 2 mission, which had successfully collected samples from the asteroid Ryugu, was being redirected toward a new target that had recently been reclassified as a dark comet. The object, designated 1998 KY-26, had been considered an ordinary near-Earth asteroid for over 25 years, but detailed analysis of its orbital motion revealed subtle, non-gravitational accelerations that qualified it as a dark comet. The discovery meant that Hayabusa 2 would provide humanity's first close-up encounter with one of these mysterious objects. The mission offered unprecedented opportunities to resolve fundamental questions about dark comet composition and structure. High-resolution imaging could reveal surface features that might indicate the source of non-gravitational forces. Spectroscopic analysis could determine whether dark comets contained conventional cometary materials or exotic compositions. Most importantly, direct sampling might provide definitive answers about the physical mechanisms responsible for their anomalous behavior. Dr. Seligman noted that the Hayabusa 2 encounter with 1998 KY-26 would provide crucial ground truth for theoretical models of dark comet physics. If the object proved to contain conventional ice and organic materials, it would support the idea that dark comets are simply comets with very low outgassing rates. If it showed unusual composition or structure, it might require new theoretical frameworks to explain their behavior. The mission also offered a test case for distinguishing between natural and artificial objects. If 1998 KY-26 proved to be space debris rather than a natural body, it would demonstrate the importance of considering technological explanations for anomalous celestial objects. The discovery of dark comets within our solar system raised intriguing possibilities for understanding Earth's early history and the origin of life. Dr. Seligman identified dark comets as potential contributors to Earth's water budget and the organic compounds necessary for biological evolution. The hypothesis was based on orbital dynamics and compositional considerations. Many dark comets follow paths that could potentially intersect Earth's orbit, particularly during the chaotic early phases of solar system evolution, when planetary migration and gravitational perturbations were more common. If dark comets contained substantial quantities of water ice and organic compounds, as their cometary classification suggested, they could have delivered these materials to Earth during the late heavy bombardment period approximately 4 billion years ago. Unlike conventional comets, which lose most of their volatile materials during repeated solar approaches, dark comets might retain their water and organic content over much longer periods. The small size of inner dark comets could actually be advantageous for delivering materials to planetary surfaces. Objects tens of meters in diameter would be large enough to survive atmospheric entry, while small enough to avoid creating globally catastrophic impacts. They could deposit their cargo of water and organics without sterilizing the planetary surface through excessive heating. This delivery mechanism might help explain some puzzling aspects of Earth's chemical composition. The isotopic ratios of water in Earth's oceans don't match those found in typical asteroidal materials, suggesting that substantial water delivery from cometary sources occurred during Earth's formation. Dark comets, with their unique properties and orbital characteristics, could represent a previously unrecognized component of this delivery process. The rapid growth in the dark comet population, from 0 known examples in 2022 to 14 confirmed objects by 2024, suggested that these mysterious bodies might be much more common than initially suspected. Dr. Seligman's analysis indicated that the 14 known examples likely represented only a small fraction of the total population. Detection biases strongly favored the discovery of larger, more active dark comets following orbits that brought them relatively close to Earth. Smaller objects, those with weaker non-gravitational accelerations, or those following less favorable orbital paths, would remain undetected by current survey programs. Extrapolating from the detected population, Seligman estimated that hundreds or possibly thousands of dark comets might exist within the inner solar system alone. This abundance would have significant implications for understanding solar system evolution, planetary formation processes, and the delivery of water and organic materials to terrestrial planets. The statistical analysis also revealed interesting patterns in the spatial and temporal distribution of dark comet discoveries. The objects showed no obvious clustering in particular orbital regions, suggesting they represented a broadly distributed population rather than the remnants of a single catastrophic event. The timing of discoveries was equally intriguing. Most dark comets had been identified within the past 2 years, despite decades of systematic asteroid and comet surveys. This recent surge likely reflected improvements in observational precision and data analysis techniques, rather than any real change in the population itself. The implications of the dark comet revolution would soon be tested by the most powerful survey instrument ever constructed. The Vera C. Rubin Observatory, scheduled to begin full operations in 2025, promised to revolutionize the detection and characterization of these mysterious objects. The observatory's unprecedented combination of aperture size, field of view, and observational cadence would allow it to detect dark comets with much weaker non-gravitational accelerations than currently possible. Its systematic monitoring of the entire southern hemisphere sky would eliminate many of the observational biases that limited current surveys. Dr. Seligman's calculations suggested that the Rubin Observatory might detect dozens or possibly hundreds of new dark comets annually. This explosion in the known population would provide the statistical samples needed to understand the relationship between different dark comet types, their origins, and their role in solar system evolution. The observatory's rapid cadence observations, revisiting each patch of sky every few nights, would also enable detailed studies of dark comet activity patterns. Researchers could monitor how non-gravitational accelerations varied with solar distance, search for outburst events or changes in activity level, and potentially detect the faint signatures of outgassing that remained invisible to current instruments. Most intriguingly, the survey might discover dark comets with properties that didn't fit either of the two known populations. Such objects could reveal additional formation mechanisms or evolutionary pathways, further expanding our understanding of small body diversity. Despite the growing catalog of dark comets, fundamental questions about their composition and internal structure remained unresolved. The non-gravitational accelerations clearly indicated some form of mass loss, but the mechanisms responsible remained speculative. The leading hypothesis involved conventional cometary outgassing at levels too low to produce visible comas. Dark comets might contain the same mixture of water ice, carbon monoxide, carbon dioxide, and organic compounds found in typical comets, but in configurations that produced much weaker activity when heated by solar radiation. This could result from several factors. The volatile materials might be more deeply buried beneath protective mantles of dust and rocky debris. The objects might have lost most of their surface ice during previous solar approaches, leaving only small internal reservoirs that could drive subtle non-gravitational forces. Alternatively, dark comets might represent a fundamentally different compositional class. They could be dominated by materials that sublimated at different temperatures or produced gases that were particularly difficult to detect. Exotic compositions involving hydrogen ice, nitrogen ice, or even more unusual materials remained possibilities. The size difference between inner and outer dark comet populations hinted at different compositional or structural properties. Larger outer dark comets might retain more volatile materials due to their greater thermal inertia and longer periods between solar approaches. Smaller inner dark comets might represent remnants of larger bodies that had lost most of their original volatile content. Understanding how dark comets formed required considering multiple pathways that could produce objects with their unusual combination of properties. The existence of two distinct populations suggested that different formation mechanisms might be responsible for creating inner and outer dark comets. One scenario involved the gradual evolution of conventional comets through repeated solar heating cycles. Each orbital pass would strip away surface volatile materials, gradually reducing the object's ability to produce visible outgassing while maintaining sufficient internal ice to generate subtle non-gravitational forces. This evolutionary pathway might naturally produce the size segregation observed between inner and outer populations. larger objects would be more resistant to complete volatile loss and could maintain dark comet characteristics for longer periods. Smaller objects might quickly transition from conventional comets to dark comets to completely inert asteroids. Alternative formation scenarios invoked collisional processes during the early solar system. Dark comets might represent fragments of larger parent bodies that were disrupted by impacts or gravitational interactions. The fragmentation process could expose internal materials with different volatile contents, creating objects with varying degrees of cometary activity. A third possibility involved capture and orbital evolution of objects that formed in different regions of the solar system. Dark comets might represent materials that condensed under different temperature and pressure conditions, giving them compositional properties that produced unusual outgassing behaviors. The discovery of dark comets had an unexpected consequence for the ongoing debate about Oumuamua's possible artificial origin. Rather than settling the question in favor of natural explanations, the findings actually strengthened some arguments for considering technological possibilities. The key insight involved the recognition that distinguishing between natural and artificial objects based on observational signatures alone might be much more difficult than previously assumed. If natural processes could produce objects that looked like asteroids but behaved like comets, then artificial objects designed to mimic natural phenomena might be virtually indistinguishable from authentic celestial bodies. This realization had profound implications for SETI research and the search for technological artifacts in space. Traditional approaches assumed that artificial objects would display obviously non-natural characteristics, regular geometric shapes, unusual compositions, or behaviors that violated known physical principles. But advanced technological civilizations might deliberately design their artifacts to appear natural, either to avoid detection or to minimize interference with naturally occurring processes. Such objects might mimic the spectral signatures, morphological characteristics, and dynamical behaviors of natural bodies while serving technological functions. The dark comet phenomenon demonstrated that nature itself produced objects with ambiguous properties that challenged traditional classification schemes. In this context, arguing for artificial origin based on unusual behavior became both more difficult and potentially more significant. The rapid expansion of the dark comet catalog highlighted both the promise and the challenges of modern astronomical surveys. Advances in detector technology, data processing algorithms, and systematic observing strategies had enabled the discovery of increasingly subtle phenomena that would have been impossible to detect just a few years earlier. But these same advances revealed how much remained hidden in the solar system's small body population. Each improvement in observational sensitivity uncovered new categories of objects with properties that challenged existing theoretical frameworks. The dark comet story illustrated this pattern perfectly. Objects showing non-gravitational accelerations had been present in survey data for decades, but the systematic analysis needed to identify them as a distinct population had only recently become feasible. How many other categories of mysterious objects remained buried in archival data, awaiting recognition? The challenge extended beyond simple detection to characterization and understanding. Even with 14 confirmed examples, fundamental questions about dark comet origins, composition, and evolution remained unanswered. Each new discovery raised additional questions about the diversity and complexity of small body populations. Future surveys would need to balance breadth with depth, monitoring large areas of sky to detect rare phenomena while gathering sufficient detail to characterize newly discovered object types. The Vera Rubin Observatory represented a major step toward achieving this balance, but even its unprecedented capabilities would reveal only a fraction of the solar system's hidden complexity. The relationship between dark comets in our solar system and interstellar visitors like Oumuamua remained one of the most intriguing aspects of recent discoveries. Both categories displayed similar observational signatures, non-gravitational acceleration without visible outgassing, yet they represented fundamentally different populations with different origins and histories. This convergence suggested that the physical mechanisms responsible for these behaviors might be more common than previously recognized, whether the underlying processes involved conventional cometary outgassing at undetectable levels, exotic material compositions, or entirely different physical phenomena. They appeared to operate across a wide range of cosmic environments. The implications extended to our understanding of interstellar space and the objects that populate it. If dark comet-like behavior could result from natural, evolutionary processes, then future interstellar visitors might display similarly puzzling characteristics without requiring exotic explanations. Alternatively, the similarity between dark comets and Oumuamua might reflect common formation or processing mechanisms that operated in both our solar system and the interstellar environments where Oumuamua originated. Understanding this connection could provide insights into the cosmic processes that shape small body populations throughout the galaxy. The potential role of dark comets in delivering water and organic compounds to early Earth added a biological dimension to their study. If these objects had indeed contributed to Earth's inventory of life-supporting materials, then understanding their properties and distribution might provide insights into the probability of life emerging in other planetary systems. The scenario was particularly intriguing because dark comets appeared to combine the best characteristics of both asteroids and comets for biological delivery. Like asteroids, they could potentially survive atmospheric entry without complete disruption. Like comets, they presumably contained substantial quantities of water and organic compounds. But unlike conventional comets, dark comets might retain their volatile cargo over extended periods without losing it to solar heating. This stability could allow them to deliver pristine samples of early solar system chemistry to planetary surfaces long after conventional comets had been depleted of their most interesting materials. The size distribution of dark comets also favored biological delivery scenarios. Objects tens to hundreds of meters in diameter would be large enough to carry substantial chemical payloads, while small enough to avoid sterilizing planetary surfaces through excessive impact heating. If similar populations of dark comets existed in other stellar systems, they might represent a previously unrecognized mechanism for distributing the chemical precursors of life throughout galactic space. This possibility added astrobiology to the growing list of scientific disciplines with stakes in dark comet research. The dark comet revolution represented just the latest example of how modern astronomical techniques were revealing hidden complexity in familiar cosmic environments. The same technological advances that enabled the discovery of exoplanets, the detection of gravitational waves, and the imaging of black holes were now uncovering mysterious new categories of objects in our own solar system. This pattern suggested that the current era would be remembered as a golden age of astronomical discovery, when improvements in observational capabilities far outpaced theoretical understanding. Each new survey, each upgraded instrument, each refined analysis technique revealed phenomena that challenged existing models and expanded our conception of cosmic diversity. The dark comet story embodied this trend perfectly. The objects themselves had been present in survey data for decades, but recognizing them as a distinct population required sophisticated analysis techniques that were only recently developed. How many other hidden populations remain to be discovered in archival observations? The implications extended far beyond dark comets to the entire enterprise of understanding cosmic complexity. The universe appeared to be far richer in diverse phenomena than anyone had imagined, with new categories of objects and processes emerging from improved observations on a regular basis. As our extended journey through the mysteries of Oumuamua, the revelations of 3I ATLAS, and the discovery of dark comets draws toward a close, one truth becomes abundantly clear. The universe is far stranger and more complex than we had imagined when that first interstellar visitor appeared in our telescopes 8 years ago. Each answer we have found has revealed new questions. Each mystery we have solved has uncovered deeper puzzles. The hydrogen outgassing theory may explain Oumuamua's acceleration, but it doesn't account for the behavior of 3I/ATLAS. The discovery of dark comets provides context for mysterious accelerations, but raises fundamental questions about the diversity of small body populations. We now know that our solar system contains at least 14 objects that look like asteroids but behave like comets, divided into two distinct populations with different characteristics. We know that interstellar space harbors ancient wanderers over 7 billion years old, carrying chemical memories from epochs when our galaxy was young. We know that objects can survive million-year journeys between star systems while retaining the volatile materials needed to display vigorous cometary activity. Yet for all these discoveries, fundamental questions remain unanswered. We still don't know what Oumuamua really was, whether its acceleration resulted from hydrogen outgassing, exotic composition, or something else entirely. We don't understand why some interstellar objects show non-gravitational forces while others follow purely gravitational trajectories. We can't explain how dark comets form, what powers their mysterious accelerations, or whether some of them might actually be technological artifacts. The upcoming years promise to bring partial answers to some of these questions. The Vera Rubin Observatory will discover dozens of new interstellar objects and hundreds of dark comets, providing the statistical samples needed to understand population characteristics and test theoretical models. The Hayabusa 2 mission will provide our first close-up look at a dark comet, potentially revealing the physical mechanisms responsible for their behavior. Space-based telescopes with unprecedented sensitivity will enable detailed spectroscopic analysis of faint objects, revealing compositional details that remain hidden from ground-based observations. Advanced computational models will simulate the formation and evolution of small body populations under different conditions, testing scenarios for creating the observed diversity. But perhaps most importantly, these discoveries have taught us to expect the unexpected. The universe has already surprised us with Oumuamua's mysterious acceleration, 3I/ATLAS's ancient age, and the existence of dark comets in our own solar system. What other surprises await discovery in the cosmic wanderers still approaching our telescopes? The age of interstellar astronomy and dark comet science has only just begun. As our detection capabilities improve and our theoretical understanding deepens, we can be certain that more mysteries will emerge to challenge our assumptions and expand our knowledge of the cosmos. Somewhere in the darkness between the stars, ancient objects continue their epic journeys, carrying within their structures the chemical and physical records of cosmic processes spanning billions of years. Some are natural artifacts of planetary formation and galactic evolution. Others might be something else entirely. The universe, it seems, has many more messages to deliver to those patient enough to observe, bold enough to theorize, and humble enough to admit that the cosmos still holds secrets beyond our current understanding. The greatest discoveries may still lie ahead, hidden in the vast spaces between the stars, waiting for the next generation of telescopes and the next breakthrough in our understanding of these cosmic messengers from afar.